Okay, so we just spent the last half hour catching up on the forum, and thanks everybody for sharing your waste streams. And hopefully I gave a few pointers on how to kill that last little bit of waste. And we've been talking a lot also recently, well, Sean just mentioned the fact that he got 2 cents per pound for tin. What I want to get into right now is looking at embodied energy. Obviously, we pay to have energy delivered to us, and the example that I'm going to give today is looking at embodied energy of plastics. I've got this one problem that I myself really need to tackle, so I was going to use class time to just do that and show you how I need to struggle with this professionally. So we're going to do a plastics exercise looking at embodied energy of plastic and try to determine from a recycling technology standpoint whether or not it's a good idea to put additional money into plastic and sort of where the break-even point is. Because when you take your tin and your metals out to Pacific, they're doing the same thing. Like what can we really afford to pay this person? We want to give them something. We want to incentivize the consumer to come bring the materials to us because, yes, we're going to make some money on the back end, but if we pay them too much, that cuts into our profit. If we don't pay them enough, nobody's going to show up. So there's always some little sweet spot there in the finance. So that's what we're going to work on today for embodied energy problem. Okay, so let's hop out. And the last time I looked at Wikipedia, there were actually some pretty good little figures. There is one. Oh, there's two. I'm gonna start with energy density, and then go to embodied energy. So let's go to the wiki on energy density. And this is typically, and I like to look at this figure right here because it's going to show us different materials on a per mass basis. So if you can't read that at the bottom, it's megajoules per kilogram. Down here is 0, way up here is 160. So this is the challenge that batteries have. They just don't have a whole lot of energy per unit mass. Hydrogen, oh my gosh, it's got all kinds. That's why we launch rockets with hydrogen. Lots of energy per unit mass. If we look along this axis, we can see that the poor battery still isn't doing so well on a megajoule per liter. That's a megajoule per volume, and that's why in general you don't see too many battery-powered aircraft, at least commercial aircraft. It's because they're big and bulky. And that is, however, why we're starting to see some large stationary batteries start to come online like Zinc Air is working on. Most of this stuff up here is, well, look at that. Polyethylene, not too bad. And that's exactly what we're going to look at today, is the embodied energy in polyethylene. So let's write these two numbers down. And then we'll also go back to the embodied energy and see how the energy density and the embodied energy stack up on polyethylene, because that's what we're going to focus on in terms of our own little recycling technology problem today.
What does embodied energy mean?
We'll get to that one quick sec. So we're going to do energy density. And embodied energy. And they are slightly different things, energy density versus embodied energy. So let's look at energy density first. So polyethylene, I'm going to call that 45 megajoules per kilogram. Polyethylene, 45 megajoules per kilogram. And and I'll just call it 45 megajoules per liter too. and 45 megajoules per liter. If you were to eat polyethylene, if your body could metabolize polyethylene, how much would you have to consume each day to live? That's all you're eating. Remember Energy 101? So one human power, one human energy per day. Yeah, you're running about 100 watts. It's 10 megajoules. So you can look at this and say, well, gosh, if I had a quarter liter, if I had 250 milliliters, 1 cup, 8 ounces of polyethylene would be enough to fuel me for the day. So 8 ounces PE per day. Now, we cannot metabolize polyethylene. We cannot metabolize cellulose, but just a little scale for you there. Okay, 45 megajoules per kilogram. Now, let's see how the energy densities compare with the embodied energy of polyethylene. And before we get too much started, or too much further here, this is what ethylene this is what ethane, oh, that's what ethane looks like. And we'll go and look at the actual molecular structure of polyethylene. Pretty exciting, huh? It's just carbon and hydrogen is all it is. It's just one big long strand. And so what I just drew there was the ethane molecule or ethylene molecule with two carbon bonds. So when you go from this ethylene monomer into this polyethylene polymer, that's all it is. This guy is a gas, a lot like methane is a gas. When it is compressed, cooked, processed, etc., it becomes a liquid polymer. Nice thing about it, for fairly low temperature. So the embodied energy is going to tell us how much energy goes into going from this into that. So let's take a look at embodied energy now. Gypsum, plywood, bitumen, slate, wool, glass, cork, cellulose, timber, marble, concrete. Here's polyurethane, and let's just see what those numbers are for polyurethane. Megajoules per kilogram to make polyurethane. 101 and 88. So let's just call it 100 megajoules per kilogram. Oops. Embodied around 100 megajoules per kilogram. Let's see if we can actually find polyethylene down here. Most of these hydrocarbons are going to be pretty similar, pretty ballpark. Slate, bitumen, plywood, plastic. PVC, again, is kind of up there, close to 100. Vinyl flooring is north of 50. Wallpaper, iron, lead. I ran these numbers before on PV panels, crystals, and the numbers are not doing the thing justice. As it turns out, the embodied energy in PV cells is astronomically higher than a lot of these other materials, just because of how the processing that goes into it. I mean, these things are being built sort of one atom at a time under tremendous heat. So let's just see if we can look a little bit more. Well, and let's just read the Wikipedia definition of it. So it's the sum of all the energy required to produce the goods and services. So the harvesting, the heating, the processing, all that stuff. That's what it is. And so by the time you've got a kilogram of this material, you've pumped, well, sometimes as much as 3 times its energy density into it, right? So think about, the energy density of a gallon of gasoline. It's sort of there, ready to go, ready to be consumed, but to become that gallon of gasoline, it had a lot of embodied energy go into it. So the fact that it's now ready to be used as energy, there's a cost of doing business. And if you remember back to 101, there's this whole energy returned on energy invested thing. So you can think of the embodied energy as more or less the energy invested. That's how much you had to spend to get to this pure substance. And if you look down here, what are some of these? What is polyurethane insulation used for? Well, it's used to save energy. So you had to put some in, but if you put it in the right place, in the long run, you're not going to have to burn as much fossil fuel to keep the house warm, right? So I don't see the exact number, but let's just kind of work under the assumption that the embodied energy going into polyethylene is at least equal or perhaps double that of its energy density. And it's going to vary. There's no standard process. And you could also imagine from an industry standpoint, you're going to want to minimize that embodied energy as much as possible, right? Because you're going to have to spend money to process the stuff in the first place. So it's in industry's best interest to minimize that. And I guess since we're talking about it, if you look up at some of these others, aluminum is quite high. And so in general, you can see that if you can get away with using a plastic with a lower embodied energy than an aluminum, it's going to save you money on the front end. Okay. All right. Well, let's do a little math here now, and we're gonna take polyethylene, and it can either be LDPE or HDPE. LDPE versus HDPE. Let's just look at that. LDPE versus HDPE. That's more or less, and I'll just kind of draw it schematically like this. In an LDPE, the chains are relatively short, and in the HDPE, the chains are going to be longer, and that more or less affects the mechanical properties. And you can go out and grab a HDPE bag versus an LDPE. This one's just going to be more resilient. It's just going to have better mechanical properties. No surprise there. And you can also see that there's going to be more embodied energy going into it, breaking those double bonds of the ethylene, and sticking into this polyethylene. Okay, now let's look at energy density, because what we're going to do is a waste to energy exercise. And I'm going to take this. Well, first of all, what's the approximate density of polyethylene? Anybody know off the top of your head? The density of plastic? Most plastics have a specific gravity of 1. If you, and it's not that surprising. Go out and look in the river, the ocean, or some bay. The plastic's kind of sitting there floating, isn't it? It's about the same density as water, sometimes slightly less. That's why you see it at the surface. So we can very easily convert kilograms to liters, because 1 kilogram of water equals 1 liter of water. Same thing with plastic. A kilogram of squished anyway. And if you remember from the recycling center, they've got this giant chicken wire bin where they're sort of throwing the plastic in at very low density. Once it goes into the baler, you're hitting densities about that of water, about 1 kilogram per liter. So that's the physical density. Now, 45 megajoules per kilogram. How much electricity is this, and how many dollars is that electricity worth? So I'm just going to take a quick break. Let's just solve this problem for 5 minutes. Sean, maybe turn the lights on. I want you to tell me. I want you to turn this into kilowatt hours, and then I want you to turn it into dollars for me. So just kind of a straightforward NRG 101 problem. So hit that. I'm going to pause, and then we'll get back.